Welcome to Integrating Science, Reading, and Robotics across grades 3 through 8 in the STEM education era. I am Anna Newley, a teacher from Sonoran Science Academy, Phoenix. I've been working with Dr. Dinez's team at UNLV for the past few years, and today I will be presenting our work on STEM and robotics integration. In this presentation, we will describe our attempts to teach integrated STEM units to grades 3 through 8 students based on 5 different articles. The first two articles describe how we engaged grades 3 through 5 elementary students in two different engineering design challenges, the soda can crusher design and the trash grabber design, by using our engineering design model. The third article summarizes how we taught epistemological aspects of engineering using picture books within an engineering design challenge. The fourth article illustrates how students in groups of 2 or 3 created biomimetic robots with coding. The fifth article details how students built an animatronic zoo showcasing a particular biome and animals living in it by using computational thinking. Federal and state governments heavily invested in STEM education, driven largely by poor science and math performance of American students in international assessments, such as the Program for International Student Assessment and in trends in international mathematics and science study. Some cite that the policy related to reporting annual yearly progress under the No Child Left Behind Act of 2001 adversely affected the opportunities to learn science in elementary and middle grades, and this particular Bush-era legislation is blamed for the poor performance of American students in the international science and math assessments. Both Presidents Obama and Trump emphasized STEM education, including computer science, as a priority for the United States because the number of college graduates with STEM degrees is perceived as an important factor contributing to the global competitiveness of the United States. From the federal government's perspective, increasing the number of STEM graduates is a primary goal of STEM education. However, improving the quality of STEM education and achieving overall STEM literacy for the general public should specifically be targeted. Bybee 2013 defines STEM literacy as an individual's knowledge, attitudes, and skills to identify questions and problems in life situations, explain the natural and design world, and draw evidence-based conclusions about STEM-related issues. It's the individual's understanding of the characteristic features of STEM disciplines as forms of human knowledge, inquiry, and design. It's the individual's awareness of how STEM disciplines shape our material, intellectual, and cultural environments. And it's the individual's willingness to engage in STEM-related issues and with the idea of science, technology, engineering, and mathematics as a constructive, concerned, and reflective citizen. STEM refers to 4 disciplines, but the acronym is generally interpreted to mean science or math rather than technology or engineering, because only science and mathematics are included oftentimes in school curriculum. Even professionals in STEM-related fields do not have a clear understanding of the acronym. Ackerson et al. 2018 shared similar sentiments about the meaning of STEM, and Bybee 2013 also suggested that the meaning of STEM is ambiguous and it varies across educational contexts. Hence, STEM is often seen as a political acronym with educational implications. Despite the STEM acronym's political connotations, it quickly became an educational heuristic suggesting ways of organizing and delivering instruction involving the combination of at least 2 of the 4 disciplines. Vasquez, Snyder, and Comer 2013 provided an operational definition of STEM education as follows. STEM education is an interdisciplinary approach to learning. It removes the traditional barriers separating the 4 disciplines of science, technology, engineering, and mathematics and integrates them into real-world, rigorous, and relevant learning experiences for students. They also provided the following principles to guide the development and delivery of integrated STEM units. 1. Focus on integration. 2. Establish relevance for the students. 3. Emphasize 21st century skills, which is accessing information when needed and how students use that information creatively to solve problems and communicate ideas and concepts collectively. Teamwork and collaboration, along with critical thinking, problem solving, creativity, and communication, collectively are known as 21st century skills. 4. Challenge your students. And finally, mix it up. Allow for a variety of outcomes in the STEM units. In part 1, we engaged elementary students grades 3 through 5 in designing soda can crushers for 5 weeks, 3 hours per week, in a Saturday STEM program. We thought that addressing a real-world problem such as finding an effective way to store soda cans for recycling would sustain our students' interest during the engineering design process. Students surveyed people in their neighborhood and collected data to find out if they would buy a soda can crusher, what impacts their purchasing decision, and the budget range that influenced their decisions. They also Googled the online e-marketing resource to see the produced soda can crushers. Students were provided criteria and constraints such as ease of use, reliability, portability, storage space, and aesthetics before they start designing their soda can crushers. First, they brainstormed about possible soda can crusher design ideas. Students were encouraged to make quick sketches of their design idea to be able to better communicate their thinking. Then they agreed upon one design idea as a group, and they did a technical drawing of that particular design idea. After completing the technical drawing, each group started building their own soda can crusher. Students in each group iteratively improved and revised their designs after testing. When each group finalized their designs, they evaluated each other's soda can crushers based on the criteria and constraints provided at the beginning of the engineering design challenge. During soda can crusher design, students also read books aligned with the phases of the engineering design process. The soda can crusher design has also natural connections to scientific concepts of force. Each soda can crusher is either operated by a push or pull force. Students start to appreciate the inverse relationship between the force needed to crush the soda can and the length of the lever applying the push or the pull force. Students started to use mathematics and computational thinking in describing the relationship between the force needed to crush the soda can and the length of the lever applying the force. This particular engineering design activity also naturally lent itself to math integration. For example, students drew scaled bar graphs to represent their needs analysis data with several categories. One bar graph represented the number of people who said yes, no, or maybe to the question, do you need a soda can crusher? This activity also gave students ample opportunity with practicing measurement skills while building their soda can crushers. We used the same engineering design model to engage elementary students grades 3 through 5 in the designing mechanical trash grabbers for 5 weeks in a Saturday STEM program. The mechanical trash grabber design challenge was similar to the soda can crusher design challenge described on the previous slide. Science, math, and reading integrations that were made in the soda can crusher design challenge were also made in the mechanical trash grabber design challenge. In addition to these integrations, we also integrated 3D design and printing to the mechanical trash grabber design activity. We asked our students to design and print at least one moving piece of their mechanical trash grabbers. We introduced our students to 3D design with a cloud-based application called Tinkercad. After students finished their 3D designs in Tinkercad, they printed them using the MakerBot Replicator Plus 3D printer. Students should experience the engineering design process in their science classes, but the activity itself should not be enough. Students should reflect on the epistemological aspects of the engineering design process as well. Understanding the nature of science is considered an essential component of science literacy, since it provides insights into the development of scientific knowledge. Similarly, the nature of engineering should be considered an important component of larger STEM literacy because it helps people to appreciate creative, subjective, tentative, social, and sociocultural aspects of the engineering design process while engineers develop solutions to human problems. Holding adequate nature of engineering views can positively impact the knowledge and development, diverse interpretation of problems, and informed problem solving techniques through engineering design. From this perspective, the nature of engineering should be an integral part of any engineering design activity. Explicit reflective instruction purposefully makes the nature of engineering ideas visible to the learner by drawing learners' attention to the relevant nature of engineering aspects through discussion and reflection. This is similar to explicit reflective instruction suggested for teaching the nature of science. While the explicit part of explicit reflective instruction refers to making nature of engineering aspects visible to the learner, the reflective part refers to encourage learners to revise their nature of engineering ideas in light of new ideas they encounter. This article describes how we integrated reading picture books into engineering design process and how we use these books to generate explicit and reflective discussions around the nature of engineering ideas. This reflective approach intentionally drew students' attention to the relevant nature of engineering ideas while students are engaged in the engineering design process. Educational robotics gained significant popularity in pre-college engineering education with the release of Next Generation Science Standards and CS for All initiative. Educational robotics enables teachers to address computer science concepts and practices as well. Teaching computer science integrated with STEM provides students a more authentic representation of contemporary science, and it enables students to acquire marketable skills for future employment. Additionally, conducting scientific research is increasingly becoming dependent upon computing. Students' access to computer science concepts and practices can be improved by integrating computer science concepts and practices with STEM disciplines. This can also help address the growing need to expose students to computer science concepts and practices so that they can utilize computational tools as future scientists and engineers. The Next Generation Science Standards acknowledge the importance of computation in science education by including computational thinking as one of 8 science and engineering practices. A number of researchers also recommended the integration of computational thinking into K-12 education. Educational robotics often provides an array of learning experiences that are complementary to integrated STEM education, mimicking joints and muscles in the skeletal system. We offered a 10-week extracurricular educational robotics club for students in grades 6 through 8. We chose to use BirdBrain Technologies' Hummingbird Robotics Kit. Students were required to construct celebrity statues by using cardboard and glue. We helped students code their celebrity statues by using Snap programming language. Snap is a visual and powerful programming tool that can work with Hummingbird robotic sets. Biomimicry can be defined as using movement and behavior of nature to design solutions to human problems. Particularly considering biomimicry allowed students to explore the human skeletal system with joints and muscles and understand the concept of movement. Moreover, we engage students in meaningful way by integrating science, engineering, and computer science. They learned scientific vocabulary and created a moving model of the human body with the support of an educational robotics kit. In this engineering design challenge, students worked in teams to design biomimetic robots that mimic the behavior of humans by using iterative design. This activity followed Bybee 2004 5E learning cycle and engaged students in a socially relevant issue by designing an animatronic zoo. The animatronic zoo is expected to provide educational affordances of a real zoo without resorting to keeping animals in captivity away from their natural habitats. In the first meeting, the students were engaged by a mock video call asking students to respond to a client's request about building an animatronic zoo so that people could still learn about the animals without animals leaving their natural habitats. In the next session, the students researched about different biomes and animals living in them. Then each group selected a different biome and created an animatronic zoo, showing the characteristic of that particular biome and animals living in it. By using the engineering design process, students designed a zoo from everyday materials and placed 3D models of 5 animals that could be found in that particular biome. BirdBrain Technologies' Hummingbird Robotics Kit was used in this activity as well. We helped students code their animals by using Snap programming language integrated with the Hummingbird Robotics Kit. For example, in the forest biome, bears roar with a sensor if people got too close. Model rabbits hopped around a pond, and a raccoon climbed up and down a tree. And the forest glowed green with LED lights. This activity provided us the opportunity to teach about life science concepts integrated with computing, engineering design process, and robotics. All STEM activities that we summarize in this chapter are well aligned with the principles to guide the development and delivery of integrated STEM units suggested by Vasquez, Snyder, and Comer. 1. Activities meaningfully integrated 2 or more STEM disciplines. 2. They were relevant and engaging to the students. 3. They all required teamwork, problem solving, creativity, and communication skills. 4. STEM activities were challenging, but students were able to complete them with appropriate scaffolding. And 5. STEM activities had a variety of outcomes. One caveat with these STEM activities is that rather than an actual classroom, these activities were all taught in an after-school program setting. Nevertheless, the activities which would likely be just as effective in an actual classroom instruction that focus on STEM integration. The next generation science standards explicitly included engineering design process and acknowledged the importance of computation in science education by including using mathematics and computational thinking as one of 8 science engineering practices. The NGSS encourages integration of STEM disciplines and computational thinking. However, teachers need professional development to successfully develop and teach integrated STEM and computing units in their own classrooms. Without appropriate professional development, federal and state level STEM education campaigns cannot make an overarching impact in the classroom level. The influence of STEM education campaigns are more likely to remain within the confines of an after-school STEM program if teachers continue to teach STEM disciplines in silos. Introducing STEM and computer science at the pre-college level is necessary to improve students' problem-solving skills. It is also important to spark students' interest in STEM before they develop stereotypes towards STEM and CS, careers that negatively impact the attitudes of underrepresented groups and female students towards these fields. More and more of the future is defined by innovation through STEM and CS. And all students should be exposed to STEM and computer science and then decide whether or not they want to continue. By exposing students to STEM and CS in early grades, there is a greater opportunity to improve their STEM literacy and help make them more informed in decisions of their career for the future. Without an enriching, integrated STEM learning experience in K-12 education, students lose the occasion to realize the potential of STEM and computer science in their development and possible career path. The following are some links to our articles where you can get more information about how to integrate STEM and robotics into your elementary and middle school classes. And finally, thank you so much for listening. If you have any questions, our contact information is in the top corner. We appreciate your time and good luck to you integrating STEM into your own classrooms. Thank you so much.